Hey everyone, Mr. Fransky here again. Today we're going to be talking about 9.2b, which kind of expands on this idea of Taylor series. We're going to talk about the Maclaurin building blocks that AP requires you to know. And so let's just jump in. So from 9.2a, just a reminder for the formulas for the Maclaurin series and the Taylor series, centered at x equals a. So Maclaurin series, remember, you just do all of the values at 0. So you f of 0, f prime of 0, f double prime of 0, f triple prime of 0. Then you multiply by each x and divide by the same n factorial, right? So f double prime of 0, x squared over 2 factorial, f triple prime, x cubed over 3 factorial. And in general, the nth derivative times x to the n over n factorial. You understand it at x equals a. Then you have to remember to plug a into the function every time. And you have to remember to subtract the a from each one of your x's, right? And this is, the useful part there is that it will, predict the function well or mimic the function well close to a as opposed to just close to 0, which is what the Maclaurin series does. Alright, so, I know the last couple of videos I made have been long. I think this one actually has the potential to not be like 35 minutes, so we'll see how it goes. Alright, so, the work here, I want you to do a few things. Find the Maclaurin series for e to the x. So the last, video we did, sine x and cosine x. E to the x is kind of the other big one that, AP expects you to know. So I just want you to do some derivatives. Should be a pretty quick one, I hope. Let's just write the first 4 terms of the sigma notation for that guy. And then the Taylor series for e to the x centered at x equals 2. So if you need to go back a slide and kind of take a look at how you're going to do that, you can take a look at that. First 4 in sigma again. And then letter C, this is a very common question that AP likes to ask. They give you a Maclaurin polynomial and they ask about the derivatives, which should be pretty easy, right? Based on the formula, you should just be able to kind of steal them from the formula, but there are some that are a little sneaky. So if this is the 5th order Maclaurin polynomial, I get named with T because Taylor series centered at 0, same thing as Maclaurin. Is this polynomial right here. I want you to pick out for me the different derivatives. So I want you to find f of 0, f prime of 0, f double prime of 0, etc. up to the 5th derivative of 0. So you're going to try these on your own, you can. I'm just going to jump in and do them so you can pause the video if you want to. Alright, so the Maclaurin series for e to the x, which can use the formula, right? So we're going to need f of 0, we're going to need f prime of 0, we're going to need f double prime of 0, and thankfully with e to the x, it's its own derivative all the time. So this is all of these. In fact, the nth derivative of e to the x is just e to the x, so it's going to be e to the 0. All of these are 1. This kind of comes back to the problem we did in the last video where we just were trying to find that thing where all the derivatives were equal to 1, and we're trying to find a polynomial for it. So the Maclaurin series, that means it's just going to be the powers of x and the factorials, because we're just going to have 1s all over the place, so we don't even have to think about them. So e to the x would be 1 plus x, right? 1x technically, and then 1x squared over 2 factorial, 3x squared over 1x squared over, 1x cubed over 3 factorial, right? They're all 1s in the front. In general, it's just x to the n over n factorial. One of the cool things about this is e to the x should be its own derivative, and it should be its own antiderivative as well. And you can check that. You can check to see that if it's true just by doing this term by term. So if we do the derivatives here, the 1 disappears. Derivative of x is 1. Derivative of x squared over 2 factorial, the 2 will come down and cancel with the 2 on the bottom. We'll just have x there. The 3 here will come down and cancel with the 3. We'll have x squared over 2 factorial. Basically, everything slides over one position. And someone mentioned to me the other day, they said, well, wait, but doesn't mean there'll be like one less term? Well, but there are an infinite number of terms. So one less term doesn't matter. There's still an infinite number of terms. So every term will have to be replaced by kind of the next term, which is kind of cool. If you antiderive, you would get x, and then x squared over 2, and then x cubed, there'd be a 3 on the bottom, so you'd have 3 factorial, x to the 4th over 4 factorial. And everyone's like, wait, what about the 1? Well, plus c could be anything you want, right? And if you make it a 1, it'll give you back e to the x. And you can make it whatever you want, but if you want to think about e to the x being its own derivative, you have to make it a 1. So let's take a look at the graph of this. And this graph is kind of similar to the sine and cosine ones that we saw the other day. So I've got e to the x graphed. And I'm going to actually turn this off for a second. We're going to start with kind of very simple, just 1 plus x. So there's our kind of linear approximation of e to the x, and it's perfect right at x equals 0, but it's not good anywhere else, right? It's okay close to 0, but it gets bad very quickly. So now if we start adding more terms, so if we do 1 plus x squared over 2, we now have a parabola, right? And it looks like it kind of goes through e to the x, okay? But it's better than the last one was. And now if we go to the cubic, now we actually start doing a pretty nice job close to 0, right? So we are really with the function like -1 to 1 maybe, and even a little further over on the right. And now as we keep adding more terms, of course, like we've seen before, it starts to get really good. Like over to the right here, it's really doing a nice job. To the left, we're only good to maybe like -2 right now. And as I did before, got my sigma notation. I'm going to start letting this b get bigger and bigger and bigger. And you'll notice The right side looks to snap together pretty quickly. I mean, if you were to look higher up, there'd probably be a pretty good gap even here. But the further off you to the right you go, there'd be a bigger gap, right? But as we let this go, I like to watch this one because that tail on the left kind of whips around. And pretty quickly, it moves to the left and gets better and better and better. This is actually one of those that converges for all real numbers, right? So no matter what you wanted to do, if you wanted to approximate e to the negative 35, obviously right now 55 terms is not enough to do that. But if you keep going, I don't know if I'll be able to get there before it freaks out. We'll find out. 39 was still okay. 110 terms. Yeah, we still got a function. Let's see if it'll go a little further. Nope. So it freaks out right about where I said I wanted to approximate it, which is funny. Alright, so anyway, even though decimals can't handle it, it truly does converge for all real numbers. And we don't really know why that's true yet. We haven't talked about the error and where kind of intervals of convergence are good for anything except for geometric series. But if you take my word for it now, e to the x, sine x, and cosine x are kind of three very special and very important functions that converge for all real numbers, which is kind of cool. We're going to talk about that a little bit more tonight. Okay, so there's our thing we graphed it. Awesome. So now we want to do Taylor's series for e to the x centered at x equals 2. We're going to find the first four terms, and we're going to give sigma notation. So centered at x equals 2, we need f of 2, f prime of 2, f double prime of 2. For e to the x, that's always x squared, or e squared, excuse me. So we have e squared for our first term, e squared times x minus 2, e squared times x minus 2 squared, over 2 factorial, e squared times x minus 2 cubed over 3 factorial, etc., etc. And so this is just e squared times x minus 2 to the n over n factorial. Always e squared, not e to the n, right? Because we're doing it centered at 2, so it's always going to be f of 2, f prime of 2, so it's always e squared. So why is this useful? Well, if you wanted to approximate like e to the 2.1, this would be a better approximation than using the center at 0, right? Because the center at 0 is good close to 0, but it's not good far away from 0. So if we want to approximate things near 2, then centering it at e squared would be good. Now, why does AP usually ask for Maclaurin series? Because we don't know what e squared is, right? That's kind of part of the reason of using Maclaurin series, because we use it at a value that's really nice. It's kind of like linearization back in chapter 3, if you remember that. Or maybe it was chapter 4. But linearization, it was like, well, let's use an easy value to be able to approximate harder values. So e squared by itself is like hard to know, right? So why don't we just use the Maclaurin series centered at 0 and use enough terms to be able to say, well, it's going to be close enough using like 6 or 7 or 8 terms to be approximating values near e squared. So AP usually asks for Maclaurin series because it's easy to evaluate the functions, and they want you to actually come up with numbers. They don't want you to have like e squareds in your answer. All right, so we're given the fifth order Taylor polynomial here, and what we want to do is find f of 0, f prime of 0, f double prime, all the way up to the fifth derivative of 0. So I think I actually changed this to Maclaurin in the problem because it's centered at 0, but the same thing. Taylor centered at 0 is just Maclaurin series. So f of 0 should just be our constant term. Looks like it's 4. It's that easy, right? F of 0 is 4. We're given it in the problem. Okay? F prime of 0 should be whatever the coefficient is in front of the x. Looks like it's negative 1/2. The second derivative should be whatever's in front of x squared. Well, wait. Where's the x squared? There isn't one. So what's f double prime of 0? It must be 0 to make that term disappear. The third derivative would be 3/8. That one I tried to kind of make obvious because it's just whatever's in front of the x cubed over 3 factorial. The fourth derivative, what's the fourth derivative? We just got x to the fourth over 4 factorial. It must be 1. So there's nothing there, so it must be 1. The fifth derivative, I think, is the hardest one, and I'll kind of take you through that. So it relies on the formula for Taylor series, and it's something like this is often asked on the free response. They really like to ask questions about things like this. They'll have some kind of a polynomial and say, what is the fourth derivative of x at 0? And, or the fourth derivative of f at 0. And people often are like, well, how the heck do I figure that out? Well, it's just whatever's in front of the x to the fourth over 4 factorial. That's it. So here are the answers I got. So we got 4, we got negative 1/2, we have nothing for x squared, and then we have 3/8, and then we have 1. Now, the fifth derivative, I think, has to be 6. And let me show you kind of the process for that. So we know that the fifth derivative of 0 times x to the 5 over 5 factorial has to equal this x to the 5th over 20. So just do a little bit of algebra. The x to the 5ths cancel, multiply by 5 factorial. 5 factorial is 120, divided by 20 is 6. That's all there is to it. Okay, so if you ever can't just think of it like what it's going to be, just set up this little thing. Well, I know this is kind of the 5th degree term of any Taylor polynomial. So we set it equal to the term, and we solve. That's it. Alright, so this is what we know so far. We know how to do geometric series. That's kind of how we started the chapter. We got a plus ar squared, ar cubed, etc., etc. And that's going to converge whenever absolute value of r is less than 1. This works whether r is in terms of x, whether a is in terms of x, whatever we got, right? This always works for anything as long as absolute value r is less than 1. So it works really well for functions that look like this a over 1 minus r, right? Lots of functions don't look like that. In that case, you have to use Taylor. The next thing we learned was the nth term test. Nth term test tells us that if the terms of the series are not approaching 0, then we're going to diverge for sure, right? This is something that doesn't come up a lot, but once in a while in a multiple choice question or something, you'll have a question on nth term test. Taylor polynomial works for any function, right? You have to take all the derivatives, and you have this polynomial that's going to mimic that function through n derivatives, or as many derivatives as you want to. Just use that many terms in your Taylor polynomial. We know that it works perfectly at the center, whether it's centered at 0 or a different number, but beyond that, we don't really know much about error. That's going to be 9.3. So what I want to talk about now is some of the building blocks that we have. So these are some that AP expects you to know. They want you to know the first two for sure. The next two I think are easy to get from using geometric series. But like the first one, this is just our standard a over 1 minus r, right? So we have a is 1, and then we just keep multiplying by x every time and adding all those terms together. So we end up adding up all of these terms, x to the n is x to the 0, x to the 1, x squared, x cubed, etc., etc. This will work as long as x is between negative 1 and 1. 1 over 1 plus x, also similar, just alternates, right? Because our r is negative x. So we've seen these two series a lot, which is why I'm not spending a ton of time on them. Right, so we have 1 minus x plus x squared minus x cubed, etc., etc. That's just the sum of negative x to the n. You can also do a negative 1 to the n times x to the n. Either way is fine. As long as you generate the series, I don't care how you do it. Also good for absolute x less than 1. Natural log of 1 plus x, this is the antiderivative of the one right above it. We did this in the Bell work on 9.2a. So antiderivative here, x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, etc., etc. We alternate. So we got a negative 1 to the n, then we have x to the n plus 1 over n plus 1, the antiderivative of this guy right here. Tan inverse, this guy relies on 1 over 1 plus x squared. So if you think about that, that would be 1 minus x squared plus x to the 4th minus x to the 6th. It's all the even powers. We went to that in depth in the last video, so I'm not going to talk about it too much. But then we anti-derive that to get tangent inverse. So we have x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. Important note about all these, no factorials. No factorial. Very common mistake is that on tangent inverse, people will throw factorials on the bottom, or on natural log as well. But these are antiderivatives of straight polynomials, right? And so there should not be any factorials on the bottom here. Note about the intervals of convergence here. Notice that we include some equals on these. We've only looked at so far the radius of convergence, and it's all been correct. Trust me. Everything we've done is above board. For sure it works between negative 1 and 1. It happens that because these are alternating series, that you can also use those boundary values. And we'll talk a little bit more about that in 9.5, about the alternating series test and alternating series error. So these are kind of the geometric things that I would expect you to know. We've kind of talked about these a lot. The next are what I call the big three. And these are the three that AP expects you to have memorized. They require you to know these. The 1 over 1 minus x and 1 over 1 plus x, I think, also are required. But these three, if you're going to learn 3 Maclaurin series, if you're going to make flashcards about something, this is definitely a thing to make flashcards on. So we've derived all 3 of these in the last couple videos. E to the x we did today, right? It's just 1 plus x, x to the 2 factorial, x to the 3 factorial. So it's x to the n over n factorial. You got to know that. And this works for all real numbers. If you want to approximate e to the negative 75 or e to the 132nd, as long as you use an infinite number of terms, there will be an exact equality. This is an exact equality. Left side and right side are exactly the same. Sin x, remember this is all the odd terms. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial. That's because the even terms will all be 0. When you plug 0 into sin x, you get 0. So when you say that, it's all the odds. You have x to the 2n plus 1 over 2n plus 1 factorial. So that's all the odds. Negative 1 to the n's to make it alternate. Good from negative infinity to infinity. We saw that when we graphed it. It snaps to the function really nicely all the way across all the values. Cosine is all the even ones, right? So 1 is technically x to the 0. Don't forget the 1. People always forget the 1. Or they put a 1 in front of the sin x. Don't do either of those things. So cosine x, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. It's all the even terms. So to get those, we do x to the 2n divided by 2n factorial. That's also good for all real numbers. Sine, cosine, e to the x, all good for all real numbers. That's why they're the big three. Kind of unique that, like the geometric series, we can actually say what this series converges to. It actually converges to an actual function, which is kind of cool. All right, so how do we use these? Well, once we have these down, you can use them in conjunction with other functions to build new functions, right? So for example, if we want to find the first few terms from the general term for the Maclaurin series for 2x tan inverse of x, all we do is we multiply 2x by the series for tangent inverse x. So if you know the series for tangent inverse x, here it is. You just throw 2x in front of it. Now, it's not the best thing to leave it like this. So what we're going to do is we're going to distribute that 2x in. So we get 2x squared minus 2x to the 4th over 3 plus 2x to the 6th over 5 minus 2x to the 8th over 7, etc., right? And then when you get to sigma notation, don't make it harder than it has to be. Sometimes we'll try to make it this thing. I just come back and think about this. I think, okay, well, I multiplied each of the terms by 2x, so just throw a 2x in the front, right? So I have, this is the tangent inverse just with a 2x stuck inside. If you wanted to, you could put this x with this x, and you would have 2n plus 2 on the top here. I think that's more thinking than I even want to do. I would just leave it alone and throw a 2x in front and say it's still all odd powers, and then I just have one more x. That's what's making them all even. Alright, so all I have left for you guys to do is try some on your own. I'm going to show you the first one. It might be helpful for you to see kind of how this works, because it's a little bit different than the last one. The last one we had this 2x on the outside. Here what we have is we have this 2x like on the inside of the function. So the way I think about this is you're replacing the x with 2x. So anytime you see an x in the formula for cosine, you're going to replace it with a 2x. Let me show what I mean. So cosine is 1 minus, this would just be an x squared and x to the 4th and x to the 6th. So what I did is to make cosine of 2x, I replaced all those x's with 2x's. That's all there is to it. And you could multiply these out if you wanted to. Like you could create a 4x squared here, and this would be a 16x to the 4th. This would be a, 64x to the 6th. And sometimes AP will actually give you that series, and they'll say, what function does this series represent? And you would have to figure out, oh, it's all even powers, so it's probably some kind of cosine. And then, oh, if I knock the 2's down as far as powers, I see that there's 2x's on the inside of all of them. This is cosine 2x. So if you want to try the other three here, they're all kind of like this. C, I think, is probably the trickiest on the page. But if you want to give them a shot, pause the video and then come back, we can try them together. Let's see what we get. So for e to the negative x, same deal as for cosine 2x. I'm going to replace all the x's with negative x. So see, we have 1 plus, now it's negative x, then negative x squared, then negative x cubed. So all it is just negative x to the nth power. I replaced the x in the sigma as well, just with the negative x. That's all you have to do. Or you could make it alternate, so negative 1 to the n, that would make it alternate every other, because all the odd exponents here are going to make it negative, all the evens are going to make it positive, and then you got x to the n over n factorial. Natural log of x plus 2. This one I think is the trickiest. You kind of have to think about this a little bit weird way, because we have a nice formula for natural log of x plus 1. The way I think about this is it's natural log x plus 1, where the x is then replaced by x plus 1. And then you should replace all the x's with x plus 1's. So you got x plus 1 and minus x plus 1 squared over 2, plus x plus 1 cubed over 3. That's going to continue on, right? So negative 1 to the n makes it alternate. All I did was replace the x in the formula for natural log x plus 1. I replaced it with x plus 1. The nth power over n. And I think that I actually changed this one. I had the n plus 1 on the n plus 1. This guy, your first term, in fact, this is wrong. Yeah, I have to make that n plus 1. Let me fix that. Come on. Let's make these n plus 1s. Sorry about that, guys. I fixed it on the original slide. I forgot to fix it here. It'll be n plus 1 on the bottom. Alright, much better. So now we have that, when you plug in 0, the first term you're going to get is x plus 1 to the first power, not x plus 1 to the 0. No, that wouldn't work well. Sine of x squared, replace all the x's with x squareds. That's it. So you got x squared instead of x squared cubed, x squared to the 5th. This is another one where you could distribute that too if you wanted to. There's some people that really stress themselves out about making sure the power is right up here. Don't do that. Just leave this as x squared, and then do the 2n plus 1. That's all you have to do. Alright, and that is all I've got for you. Under 20 minutes, look at that. I love you guys, that's why I'm here. Have an excellent day.